Theovis, the idea made visual. Probability feels slippery and abstract, but almost every puzzle in it becomes obvious the moment you turn it into a picture.
A picture of what?
Area. Chance is area in disguise. And once you see that, even the paradox that fools doctors falls apart.
How do we draw a probability?
Draw a square with area 1. That's everything that could possibly happen. An event is just a region inside it.
So the probability of the event is the fraction of the square it covers?
That's the whole idea. Bigger region, more likely. The entire square is certainty. An empty region is impossibility. Here are two events overlapping in the square of all outcomes. The chance of A or B is the area of their union.
And if you just add the two areas, you double count the overlap.
That's the butterfly effect, and the shape they trace is a strange attractor, never repeating, never escaping. Bounded unpredictability.
What about combining two things that both have to happen?
If they're independent, you multiply. The area of a rectangle is width times height. 2 coins, both heads, is a half times a half.
And conditioning?
Conditioning just zooms into one strip of the square and asks what fraction of that strip your event fills. That single idea becomes Bayes' theorem. Now, spread the outcomes along a line, each with a weight equal to its probability. The expected value is simply the balance point.
The center of mass of the whole distribution.
Yes, and how far the weight spreads from that point is the variance, your first real measure of risk. Put numbers on it. A bet that wins 10 one time in 5 and loses 3 otherwise.
The expected value is minus 0.4, a slow bleed on average.
But the standard deviation is over 5. The mean tells you the center. The spread tells you how wild the ride is. Both matter.
You promised a paradox. Let's have it.
A disease affects one person in 100. A test is 99% accurate both ways. You test positive. What's the chance you actually have it?
99%? Surely.
Most people, and many doctors, say that. The real answer is 50%, and the picture shows why instantly. Take 10,000 people. 1%, 100, are sick, and the test catches 99 of them.
But of the 9,900 healthy people, 1% also test positive. That's 99 false alarms.
So among everyone who tests positive, 99 are truly sick, and 99 are not. Your odds are 99 out of 198, 1/2. The rare disease drowns in false positives. Put it in Bayes' theorem, and the same answer drops out. True positives over all positives.
Both terms are equal, so the answer is 1/2, exactly what the rectangle showed.
The lesson: a test's accuracy and your chance of being sick are not the same number. Base rates matter enormously.
What if the disease were 1 in 10,000 instead of 1 in 100?
Then, The same test that says positive is almost always wrong. The few real cases are buried under a flood of false alarms.
So the rarer the thing you're hunting, the more your positive result means nothing on its own.
Which is exactly why we don't screen the whole population for very rare diseases. The math forbids it.
Can geometry run the other way? Chance giving us a number?
Beautifully. Rule a floor with parallel lines and drop needles as long as the gap. The chance a needle crosses a line is 2 over pi.
So if I drop thousands and count the crossings, I can estimate pi?
That's Buffon's needle. Randomness measuring a perfectly fixed number. Let's watch it. Each needle that crosses a line counts. The fraction that cross settles toward 2 over pi.
And rearranging, pi is about twice the number of needles over the number of crossings.
Drop enough, and the estimate creeps toward 3.14. Pure geometry, delivered by pure chance. One more counterintuitive count. How many people before 2 probably share a birthday?
Multiply the chances that each new person misses all the earlier ones, and by 23, the odds of all distinct drop below a half.
So, with just 23 people, a shared birthday is more likely than not. There are far more pairs than people, and pairs are what collide.
How does this connect to real risk?
Risk lies in the tails of the distribution, the rare, extreme outcomes. 2 bets can share the same average and feel completely different.
Because one has a fat tail of disasters, the average quietly hides.
Exactly. The expected value tells you the center. The spread and the tails tell you what can actually hurt you. Real markets are the cautionary tale. Price moves look bell-shaped until a crash arrives that the bell curve said should never happen.
Because real-world tails are far fatter than the tidy model assumes.
So a once-in-a-million event by the model turns up every few years. The geometry is exact. The assumption about the tails is what bites. One caution worth stating plainly. These clean shapes assume you actually know the true probabilities. In the real world, you usually don't.
So the bell curve can badly understate how often extreme events really happen.
Right. Respect the tails, and never mistake a tidy model for reality. So, whenever probability confuses you, draw the square. Events are regions. Expectation is a balance point. Bayes is just comparing rectangles.
And risk is the shape of the spread, not only the average.
See chance as geometry, and the paradoxes turn back into pictures. To go further, Gigerenzer on why natural frequencies make Bayes click, Kahneman and Tversky on why our intuition fails it, and Taleb on the tails.
Chance, it turns out, was geometry all along.
Draw the area, and the odds reveal themselves. If it finally clicked, subscribe. It really helps. And I'll see you in the next one.